So we'll talk very briefly about metallic bonding. We talked about how metals have low ionization energies. They will lose an electron fairly easily. So what happens in a metallic solid is each metal atom donates one or more electrons to an electron sea, like a pool of electrons or an ocean of electrons. And then what we have are metal cations surrounded by this negative sea of electrons. The electron is a little boy in the neighborhood sort of analogy. Is each of these purple places here is a house, and they sent the kids outside to play. This is back when you could do that. When I grew up, you went out in the morning and you came back when the streetlights came on, and Mom didn't worry about you at all in between. It was great. Anyway, so all of these houses have kids, and they all send a couple kids out to play, and the kids are just running wild throughout the neighborhood. But the neighborhood is united, and they're all kind of watching out for everybody's kids, right? Because it's not just my kid that's out there, but all these other kids are out there, and I'm hoping that other parents are kind of watching out for what's going on in their backyard. So that's kind of how I see that one. This bonding model explains how metals conduct electricity. So electrical conductivity requires that you have charged particles that can move. Well, the electrons here are not tied to any individual atom or ion. They are free to move, and so it'll conduct electricity. It also explains malleability and ductility. You take a chunk of metal and you hit it hard with a hammer, you might dent it, right? It's not going to shatter into pieces. If you hit this, you can move some of the atoms over and deform it, but you're not going to cause all of the attractive forces, all of the metallic bonding to break. Whereas in an ionic compound, if you put a lot of force on part of the substance, you'll cause a separation between the atoms, or between the ions, and then it literally will fall apart. But metals don't do that. Any questions about metallic bonding? Let's talk a little more about that in a future chapter. I'm not going to test you on this, but I think it's just really interesting. So we all know that the ozone layer is important, right? Do you know how the ozone layer protects us? Yeah, it absorbs ultraviolet light. So oxygen has a double bond. No, but staring at it makes me feel better. Okay, so oxygen has a double bond. Ozone has weaker bonds. We drew the Lewis structure for ozone, and it had two resonance forms, and we agree that the actual structure is a combination of those, kind of an average, and so we can think of it as a 1.5 bond here and a 1.5 bond there. These bonds are weaker than the double bond in an oxygen molecule. Question?
Is UV light, is it ionizing? Is it enough to ionize?
No.
It's not?
UV light is not ionizing radiation. So the UV light that's coming in from the sun, right here, hits this ozone layer. It can't, there's oxygen in there too. It can't break this double bond because that's too strong. But UV light does have enough energy to break this ozone bond. So when you break one of those bonds, then you get an oxygen molecule and an oxygen atom. And it has absorbed that UV photon.
If UV is not ionizing, then how does it damage?
It's a good question. So if UV can't ionize, how does it cause damage? it's higher in energy than visible light.
So does it break bonds?
You know, that's a really, really good question. I don't know the exact mechanism. But we talk about a sunburn, right? And it's like your skin got burned by heat, but it wasn't heat, it was ultraviolet radiation. So I think it's related to that, but not a biologist.
Okay.
Yeah, but that's a great question. So the oxygen molecule and the oxygen atom then will run into each other and reform ozone. And so the UV light coming at the ozone layer does not destroy the ozone layer. Anybody have any questions?